Section 2.4 is the product and quotient rules. So now we're extending beyond our basic differentiation formulas, which were the power rule, the derivative of a constant, and then the sum rule for derivatives. And we're going to extend a little bit further and first see what the derivative of a product of two functions, which are differentiable, is. And then we'll look at the product of a quotient, or sorry, the derivative of a quotient of two functions, f and g. So unfortunately, what we don't have is this. So don't write this down, don't commit this to memory, but we don't have what we would hope. We know that the derivative of the sum of two functions is the sum of their derivatives. But as a product, the derivative of the product of two functions is not the product of the derivatives. It's not something like this. We don't get to just take the derivative of each and multiply them together. It's a bit more complicated than that. At the end of this, at least at the end of these blank notes, if you've got access to those, they should be in the annotated lectures folder. We'll see a derivation of the product rule, and we'll see why we don't, we'll see why it is what it is. It turns out that we don't just multiply the product of each of these functions' derivatives, right? We don't just form the product of each of these functions' derivatives. So we don't multiply f prime by g prime. The product rule, or the derivative of this product of two functions, f and g, which are differentiable, is the derivative of f of x times g of x plus f of x times the derivative of g of x. Or in other words, we could write this in another way, f prime of x times g of x plus f of x times g prime of x. It's exactly what's written over here. Well, more or less with a little line break in it. So it's not just as simple as, again, taking the product of the derivatives. We've got to do a little bit more work. There's a more complicated formula connected to this one. And this is why it comes in this section and not the previous one. So again, f of x needs to be recognized as a differentiable function, and same for g of x. The way you choose to group these is really, it's a matter of what seems to work the best in terms of the calculation. Most of the time, it'll look pretty obvious. There'll be two different types of function. So let's go ahead and start looking at examples, and maybe some of that will become clear. So we're asked to calculate the derivative for the function y equals x cubed times cosine x. So I think clearly I've added this dot here in that notation. We might see this function written as x cubed cosine of x. Of course, we know that that means we're multiplying x cubed times that cosine of x. Okay, so clearly we could group this as an x cubed and as a cosine of x. The way to know that you're grouping things in a way that makes sense is each of the individual derivatives would be easy to take. X cubed's derivative is easy to take. It's just the power rule. Cosine of x's derivative is easy to take. It's just negative sine of x. So that's a good grouping, and that's going to work out nicely. So that's pretty much the most obvious choice anyway. So remember, the rule tells us to do the following. We take the derivative of the first function, that's x cubed, times the second function. We're not taking this one's derivative here, we're just writing it down as a factor. And then plus the first function, not taking its derivative, just writing it down as a factor, times the derivative of the second function. And so when we do that, x cubed's derivative is 3x squared, right? Power comes down, we decrease the original power by 1, times cosine x, and then plus x cubed times the derivative of cosine x, which is negative sine x. Let me clean all this up. We have 3x squared cosine x minus x cubed sine x. So that's sort of a characteristic of the product rule, right? We have a product of two functions. It's a single term. It's not a sum, right? However, we have two terms in the end once we've taken the derivative. That's a pretty common pattern to see for the product rule. It should normally, anywhere you use the product rule, it should double the number of terms that were involved. Let's move from one term to two terms here. So let's continue on. So we're asked to find the derivative of y, in this case with respect to t. It's a function of t here. So we have quite a bit going on here, right? So let's be careful with this. We have one function times another function. I think this is our most reasonable division of these functions, is to say, here's a first function in parentheses, and then a second function that it's times in parentheses. Well, the second function, t plus 5t cubed, is a polynomial. We'll just be able to use the power rule with the sum rule so we can find its derivative pretty easily. This function is going to take a little bit more manipulation in order to get it in a better place, but we remember that 1 over t squared is really just t to the negative 2. So that's this rewrite of it down here. Then I have minus 3 over t to the fourth, or minus 3 times 1 over t to the fourth, right? Minus 3 times 1 over t to the fourth. That's a way to read that. 1 over t to the fourth is t to the negative fourth. So negative 3 times t to the negative fourth is that term. So now what this has done is it's kind of ensured me that I know how to take the derivative of this function. So I've written it like this, and now I can apply the power rule to each of those terms. So remember what the product rule says overall. The derivative of this function times this function plus the first function times the derivative of the second function. So let's go ahead and do that. I don't have any ddt's or any of that stuff in the way here. I'm just saying this is our derivative, y prime. It's the derivative of this function. So we get negative 2 t to the negative 3 by the power rule. Then we have positive 12. Negative 4 times negative 3 is positive 12 t to the negative 5, reducing that power by 1. Remember, subtract 1 and do that cleanly. Remember those are negative exponents in there. Negative 2 minus 1 is negative 3. Negative 4 minus 1 is negative 5. That's how we get each of those exponents. So that's the derivative of the first function, and then simply times the second function. So just a copy of it. We don't take its derivative, we just write it there, just as the rule says and just as we did above. Now it's the first function, or plus the first function, times the derivative of the second function. Now we operate on this one. The derivative of t is just 1. The derivative of 5t cubed is 15t squared. And there we have it. We could go through and simplify all this. It doesn't ask us to simplify the answer. So this is sufficient enough. We've calculated all derivatives. We haven't left any calculus to be done. We might have left a little bit of algebra to be done. That's okay, unless we're asked to simplify the answer. So here we are. Let's continue to see the quotient rule. So the quotient rule is, well, exactly that. It's going to be applied to the ratio of function f of x over g of x, and we're looking for the derivative of such a ratio. Now, just like the product rule, it doesn't follow something simple like the quotient of the derivatives. In other words, this is not equal to f prime of x over g prime of x. That's a mistake, right, to do that. Clearly, this is not the case, right? The quotient rule is this big involved-looking thing here. And again, to understand where it came from, you'd have to see the derivation. I believe also at the end of these notes is the derivation for this formula as well. Product rule is a little easier to see, maybe a little bit less work to go through, but you could also look at the details of this if you wanted to be convinced that it's not simply f prime of x over g prime of x. So to read this one through, it looks a little bit like the product rule in the numerator here, right? But we take the derivative of the first times the second function, minus the first function times the derivative of the second function. And we're not done there anymore. We have to divide by the denominator function squared. Okay, so another way we hear this read, it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Right? To put it in more crude language, but something that might be easier to remember. All right, so 10.2, this example asks us to calculate the derivative of the given function. The function is f of v. It's equal to v cubed minus 2v square root v all over v. Okay, there's a lot going on, so let's be nice and slow and careful with this. We do have a ratio of functions, right? We have a numerator over a denominator. So we have a top function, this one, and we have a bottom function, which is just v. So there's, I guess, f and g, or numerator and denominator function for our formula. Now we want to look at this real quick. This is not quite ready for the power rule, but 2 times v times the square root of v. Remember that the square root of v is v to the 1/2 power. This is v to the first power, so it's 2 times v to the 1 times v to the 1/2 or 2 times v to the 1 plus 1 half, right? Root v is v to the 1 half. You multiply two things with the same base, and you add their exponents to get 1 plus 1 half. So now in the next line, I'm writing, well, we're looking for f prime of v overall. We want the derivative of the numerator times the denominator, as we have here, the derivative of the numerator times the denominator. I'm applying my formula from up here, right? So the derivative of the numerator times the denominator minus the numerator, or the top, times the derivative of the denominator, derivative of the bottom, all over the denominator squared, or the bottom squared, squaring v then. Okay, so I haven't taken the derivatives in the numerator yet, but I've set them up. I use my operation notation to say, okay, I'm going to take the derivative of this, but I want to make sure I get my formula correct, so I'm going to take my time, right? You don't have to take your time all the time, but as you learn these, I really recommend that you do. You try to write some of these operators down, carefully place the pieces where they go, make certain algebraic adjustments that will make these calculations more manageable, easier to see, or even feasible in the first place, and proceed from there. That way you don't make mistakes and frustrate the whole learning process. So the derivative of this expression is 3v squared for the first term, and then minus 2 times 3 halves, which 2 times 3 halves is just 3. It's a negative 3 there. And then 3 halves minus 1, well, that's 3 halves minus 2 halves. That's going to be 1 half. So here we are. 2 times 3 halves, v to the 1 half. Okay, that 3 halves came down. We subtracted 1 from 3 halves in the power and got 1 half. And there's that derivative in the works, right? We're multiplying it again by v, right? So that's that same v. It's just been moved to the front. Looks like it was forgotten initially when these notes were written. And then minus the numerator times the derivative of the denominator. Well, this is a very easy derivative to take. The derivative of v with respect to v, ddv of v, is just 1. Right? Power rule tells us that. There's an exponent of 1 there. Comes down, we have v to the 0, that's 1. Nonetheless, it's all just 1. And then if there's any simplification we could do here that's obvious, maybe we go for it. It looks like we've done quite a bit, actually. Note this, we're going to multiply v times all of these terms. We get 3v cubed minus 3v to the 3 halves, right? And that's the first two terms down here, 3v cubed minus 3v to the 3 halves. And then minus v cubed, that's this term. And then plus 2v to the 3 halves. It's this term here. Minus minus made that. Okay, and since we're here, we can combine these two terms to get 2v cubed. We have a negative 3v. Well, let's see, how did we do it off to the right? Okay, so what we realize is this. We have factors of v all over the place, right? So we can start working with this v squared in the denominator to try to simplify this. We don't always need to, and the problem doesn't ask us to simplify this, but if we needed to take another derivative of this function, a second derivative, f double prime of v, we really want it to be in a simpler form than what's currently highlighted. Okay, so we want to go ahead and try to simplify whatever we can. And in this case, what happens is this. This term and this term cancel to get 3v. These two cancel to be negative 3v to the negative 1 half. V to the 3 halves minus 2. 3 halves minus 2 is negative 1 half. We're subtracting that v squared, that power of 2. This term is negative v cubed over v squared. That's negative v. Again, the powers cancel. 3 minus 2 is 1. And then plus 2v to the negative 1 half again. 3 halves minus 2 is negative 1 half. So then we have like terms to put together, but 3v minus v is going to be 2v. And then negative 3v to the negative 1 half plus 2v to the negative 1 half is negative v to the negative 1 half. Now this is oddly put together. As I started to do, we could have combined these like terms and then these two like terms, and then done that cancellation with v squared, but nonetheless, either way works and we get to the same place. This is a nice clean version of this function's derivative. if I had to take f double prime of v, I would rather do it with this function than something like this, because this one I'm going to have to do a lot of work for. I better try to simplify that before I try to actually take another derivative of it. That can be very messy. So that's the reason to, practice simplifying these, because you will have to take second derivatives of functions like this eventually. So another example, calculate the derivative of the given function. We have y equals root t minus 1 over root t plus 1. So we just have to remember that root t is square root of t, so that's t to the 1/2 for both instances. And we're going to do the derivative of the numerator times the denominator. So derivative of this times this for our first term and our quotient rule expansion. So this expression's derivative is 1/2 t to the negative 1/2. That's by the power rule, minus the derivative of 1, which is just 0. So we have 1/2 t to the negative 1/2 is our derivative here in brackets of this term. And then times the denominator, that's that term. We'll simplify this in the next line. But we go on with the formula, minus the numerator times the derivative of the denominator. Or better yet, down here, t to the 1/2 plus 1. The derivative of t to the 1/2 plus 1 is 1/2 t to the negative 1/2. So 1/2 minus 1, and the exponent goes to negative 1/2. And then plus the derivative of 1. Well, the derivative of 1 is just 0. So again, 1/2 t to the negative 1/2 is the whole derivative here. Divide all of that by the denominator squared, t to the 1/2 plus 1 squared. Okay, now be careful. Don't forget how algebra is done, right? We can't just cancel this 2 and this 1/2 because we have t to the 1/2 and then a square on the outside. Remember, this is a binomial. There's a whole FOILing multiplication process that really needs to take place before we try to, do any simplifications here. If that was just t to the 1/2 to the power of 2 in the parentheses, then sure, it would cancel. But we have a plus 1 right here. And that blocks us from being able to do that. So just leave this term alone. I don't think it's going to go away by the time we're done with this problem. And that's typically or very often the case. So getting back to the numerator, we can make some simplifications. Namely, we can multiply each of these terms times the binomial that they're adjacent to. So we have 1/2, and then t to the negative 1/2 times t to the 1/2. Well, that just comes out to 1. They cancel. Negative 1/2 plus 1/2. Those exponents add to 0. T to the 0 is 1. And then we've got t to the negative 1/2 times 1, and that's this term right here. So go ahead and check that, make sure that works out. And then minus, now we multiply 1/2 t to the negative 1/2 times each of these terms. And of course, the first term, very similarly, is going to be 1, right? And then we're going to have minus t to the negative 1/2. Right? And now in this case, what we did with the 1/2 is we just factored it out front. It seems that everything has a factor of 1/2 in it. So we've just factored it out completely and just left it here and dealt with t to the negative 1/2 times this and t to the 1/2 times this for each of these two terms. So check those details, make sure they work out algebraically, and then pause the video if you need to, move along from there. All divided by that denominator squared. I'm not expanding that, I'm not trying to work with it. Unless I had terms in the numerator eventually that look a lot like this, I'm not going to try to do much with it. Okay, so I have 1 minus 1. I have t to the negative 1/2 minus negative t to the negative 1/2. So that's plus t to the negative 1/2 on the second half there. So 1 minus 1 is 0. And then I have t to the negative 1/2 plus t to the negative 1/2. So I have 2t to the negative 1/2. So in the brackets, all I really have is 2t to the negative 1/2. And that's times 1/2. So 2 and 1/2 cancel to 1. I just have 2 to the negative 1/2 over, again, the denominator squared. Now this numerator doesn't have a plus 1, so it doesn't look anything like the denominator, so I'd just call this simple enough. I could write it as t to the negative 1/2 times t to the 1/2 plus 1 to the negative 2, I didn't want to write it as a fraction anymore, but this is just as well. It's probably as good as that one would get. We could think about multiplying t to the 1/2 over t to the 1/2 as a form of 1, and maybe that puts a 1 in the numerator, and perhaps that's more simple down below, but that's just getting a little carried away potentially. So the overall point is to implement this quotient rule formula correctly. It's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom square. Or, in other words, as you see it in the formula at the top here. It'll take a while to get this committed to memory, but you should do enough problems over time that you don't really have to think about memorizing it anymore. You just accidentally memorize it from all the practice. Then you'll know you're in a good spot with understanding how to do this. Okay, derivatives of trigonometric functions. So it turns out we can take derivatives of the rest of the trigonometric functions. We've already seen cosine or sine and cosine's derivatives. We can go a little further and now talk about something like tangent's derivative, right? So this table tells us that tangent has derivative secant squared x. Well, let's prove that that's the case, right? And then we'll go back and address the other functions' derivatives in just a moment. So d dx, the derivative with respect to x of tangent x, okay? Well, I'd be kind of stuck here if I didn't think of this, if I didn't realize that tangent of x is really the sine of x over cosine of x. And that's a good thing to realize, because what I know is that I can take the derivative of sine x, and I also know the derivative of cosine x, and I know how to take the derivative of a ratio of functions, right? Or of a quotient of functions. It's the derivative of the top, sine x, times cosine x, minus the top, which is sine x, times the derivative of the bottom, cosine x. There's our quotient rule's numerator. And then it's all divided by the bottom squared, cosine x squared. So here's our quotient rule thrown at this right away. These are easy derivatives. Remember, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. So here we are. We have some simplification to do now. We have cosine x times cosine x is cosine squared x. We have negative sine x times a negative sine x. So that's positive sine squared x. And everything's still over cosine x in both cases, or cosine squared x in both cases. So cosine squared x plus sine squared x, there's one little trick going on here. That's the Pythagorean identity. That's equal to 1. The sum in this numerator is equal to 1. So I can replace all of that with a 1. And I have 1 over the cosine squared of x. Remember that 1 over cosine x is secant x. So 1 over cosine squared x is secant squared x. Okay, so let me move some of this out of the way. Maybe I can give a little bit more detail in this little finishing argument about how this came about. Just one last little bit of notation. I'll put an in-between equal sign. 1 over cosine x squared is this line right here. And 1 over cosine x is secant x, and squaring secant x is secant squared x, right? So there's our in-between, secant x. When you square a trig function, our notation is to take that power, or if you take it to any power, except for -1, and put it right here as secant squared x. It's a little confusing, but just remember that that's how that notation works out. So in between here will be these steps. We want to just recall some of that trigonometric notation. So a great exercise at this point would be, as a student, to say, okay, can I find the derivative of secant of x with respect to x? And the key thing to remember is what secant of x is, just like we saw above. Secant of x is 1 over cosine x. How do you find the derivative with respect to x of secant of x? Well, you write it as 1 over cosine of x, and then you use the quotient rule. The derivative of 1 times cosine x, derivative top times bottom, minus the top, which is 1, times the derivative of cosine x, the derivative of the bottom, all over the bottom squared. Cosine of x squared is cosine squared x. And you're off and running there. You just have to make some simplifications, Probably remember a Pythagorean identity in at least one spot, and then make that final move to see that the derivative of secant of x should turn out to be secant x tangent x. So hopefully you can derive that on your own. And of course, we've got the derivative of cosecant of x is negative cosecant x cotangent x. Derivative of cotangent x is negative cosecant squared x. So remember that all these derivatives exist, and these identities are true wherever the function is defined, right? Remember, some of these functions have vertical asymptotes. In fact, all of these 4 trig functions have vertical asymptotes. So they're not defined at those places where they have vertical asymptotes. So those are x values for which the derivative does not exist. But wherever it does, the derivative is, well, given by these formulas. Okay, so for a little bit of practice with trig functions, we've got first f of t here. We're asked to find the derivative of this function. F of t is sine t times cosine t. So this is a product of 2 trig functions. So be careful, right? So what we should do is take the derivative of the first function times the second function. So this is sine of t's derivative is cosine t times that second copy of cosine t here is our first term, and plus the first function times the derivative of the second. This is the product rule written down with brackets surrounding the derivative that's already been taken of the first function and then the second function in each of these pairs of brackets. So for our second term here, we have sine of t times the derivative of cosine t. Derivative of cosine t is negative sine t. So this comes out to cosine squared t minus sine squared t. And just incidentally, that happens to be equal to cosine of 2t. It's the double angle identity for cosine, but this answer is just fine. So good. Okay, now next up, calculate the derivative of f of theta. So theta is our independent variable now. We have secant theta over 1 plus secant theta. So now we have a quotient of 2 functions. And on the quotient, in the denominator, we've got a sum, right? We know how to handle that. We've already done that with root function plus 1. It was root t plus 1 previously. So that'll be fine. Remember the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So here we are. The derivative of the top. I might need to go back to the previous page and find secant's derivative, but derivative of secant theta with respect to theta is secant theta tangent theta. Now times the bottom. This is times the bottom right here. It's the first term minus the top function times the derivative of the bottom function. Well, the derivative of 1 plus secant theta, the derivative of 1 is 0, plus the derivative of secant theta is secant theta tangent theta. So here we have 0 plus secant theta tangent theta, which is just secant theta tangent theta. All right, now let's simplify this algebra. We've got to multiply this term by each of these two, and then we'll multiply this term by this term. All over the bottom squared, of course, 1 plus secant theta quantity squared. Maybe we expand that, maybe not. We'll see once we get towards the end here. So this is secant theta tangent theta times 1. Then we've got secant theta tangent theta times secant theta. So that's 2 factors of secant theta. So secant squared theta tangent theta. Take your time with that. Pause if you need to. Make sure the details check out. And then minus, we've got secant theta times secant theta tangent theta. So 2 factors of secant theta times tangent theta is secant squared theta tangent theta. We have 2 matching terms with opposite signs, so they add to 0. So now we're left with secant theta tangent theta over 1 plus secant theta quantity squared. It's not 1 plus secant squared theta like this, right? It's both of these. It's the binomial. So there's no tricks to have here, or tricks to do or chase after. We could probably throw some identities at this and manipulate this into another form. It doesn't ask us to simplify it. We don't need to do anything further with it. So this is a suitable enough simplification. Now, were we to take more derivatives of this, maybe we would pursue some kind of expansion of this and see if we can get some more cancellations. But this should suffice. As long as the calculus is done and you haven't been told to simplify it to some specific form or to meet some sort of condition, then you're all set in terms of the algebra, right? As long as there are no lingering derivatives to take that haven't been taken. So just a glimpse. I won't do the whole, well, maybe I'll sketch it. It's worthwhile. At this point, we're getting back into the abstract theoretical stuff. If you need to save time and practice these types of problems, then stop here and go back to practicing working on these things. But a quick derivation of the product rule. Why isn't the derivative of the product of two functions the product of the derivative? Well, this is how it comes out. If f of x and g of x are both differentiable functions, and we want to take the derivative of their product, as we have here, well, we write that definition down. So the limit as h approaches 0. Our function is now this, f of x times g of x. So our function of x plus h is this, f of x plus h times g of x plus h. And then minus our function, f of x times g of x, all over h. This is our difference quotient for the product of these two functions. Okay, well, we add and subtract, sort of a magical term here. G of x times f of x plus h, and added g of x times f of x plus h. So if we added the two red terms together, they'd add back up to 0, and we'd get our original expression up here, our original argument of the limit. But the reason we do that is because we're going to split this numerator over pairs of these sums. So namely, what I want to group is I want to group these two terms in a numerator over h. So here they are here, with f of x plus h factored out of them. And then likewise, I'm grouping these two terms over the numerator h, and I'm going to factor g of x out of each of these. And I get this expression right here. G of x factors out. I have f of x plus h minus f of x over h. Why did I do all of that? Well, it's because I, with some foresight, realized that I would arrive at this position right here and right here. The sum of two, the limit of the sum of two different products and quotients going on right here. So it's a bit complicated at the moment. But if I look closely at this, what I realize is that this limit exists, right? And this limit is actually g prime of x, right? As h goes to 0. That's the definition of the derivative of g prime of x, right? And we know that it exists. The product rule assumes that g is differentiable. As h goes to 0 for this function, this just goes to f of x. So this is f of x times g prime of x as h goes to 0. So there's the first term in our product rule. Now the second term, g of x, remember that it's constant with respect to h as h goes to 0, so it will just be itself. And then the limit as h goes to 0 of this, well, that's exactly our definition of f prime of x. So we know that that exists because f's also differentiable. The product rule assumes that f is differentiable. So f prime of x is equal to this. So we have g of x times f prime of x. And thus we arrive at the derivative of the product of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. And we could switch it around, so maybe it looks more like what we're used to seeing, the derivative of the first times the second plus the first times the derivative of the second. However you go about remembering, there it is. So quotient rule it's got some very similar situations going on with it. Here's the start to it. I don't believe these notes post more. Oh, they do. These will be in the annotated lectures folder. The textbook also derives this. So anybody who's really very curious about where the quotient rule comes from can follow along with this as well. It's a very similar argument to the product rule, but with a little bit more calculation to do because quotients are typically more complicated. So nonetheless, that's the product rule and the quotient rule from section 2.4.